This is the last chapter we're going to do this semester. Chapter 9 is an extension of chemical bonding. Only now we're going to add some tweaks to the valence bond theory to work out some issues that what we know up to now have not covered. And then we're going to move into the modern approach to bonding that solves all these problems. Although the previous the valence bond theory and the model that goes with it still are useful, but I'll tell you about that in a minute. how the molecular orbital theory solves a bunch of problems that aren't even addressed with the valence bond. Okay, so let me share. Here we go. Actually, come on. Here we go. I need to so this is going to be broken into two sessions. There's no way to cover all this material in the time we have left. So I've got a break built into it that is a logical place for us to stop. All right. Here's the major problem with the valence bond theory and the localized electron model. And the best illustration of this problem is the Lewis structure for methane. If you remember, the localized electron model says the electrons in a bond belong to individual atoms or they're in the bond itself. So those are either lone pairs or bonding pairs. But even then, the bond is formed by an overlap of orbitals between two atoms. So those orbitals still belong to the atoms. They just overlap. Well, if we look at the methane, right, and we use our Lewis dot structure, we end up with that. And 4 groups means what? Tetrahedral. Since there are no lone pairs here, then the electronic geometry is the same as the molecular geometry. So this is a tetrahedral molecule by the localized electron model. Here's the problem. If we're going to overlap orbitals, which orbitals do we overlap? Let's see, there's the shape. And the bond angles, of course, have been 109.5. So the electronic configuration for carbon, hydrogen is no problem, right? Hydrogen is just 1s1 for each one of them, right? Remember that? Okay, so but for carbon we have 6 electrons, and it would be 1s1, 1s2, 2s2, 2p2, 6, 2, 4, 6. Right. So for the valence bond model, the only ones we need to consider are the valence shell. So we have this 2s2, 2p2. Well, we know that the shape of the s orbital is spherical. So you can get some overlap there with a couple of hydrogens, but the p is dumbbell shaped. It gives you a different angle. Right. The s orbitals are going to be like that, and the p orbitals are going to be like that. Right, and then like that, you got to have 6 of them. So how do you get 109.5 degrees out of some overlapping here and some overlapping here? The answer is you can't. It will not work. So that's a major problem with the valence bond theory and the localized electron model. So And we know that these angles are 109.5. Right? We know that. Experimental evidence proves it. So we have to assume that all these bonds are equivalent in strength and in angles and in distance. So here's what I think it was Linus Pauling that came up with this one. Yeah, Linus Pauling. It's a concept called hybridization. Do better than that. It still works within the valence bond theory and the localized electron model, using atomic orbitals to produce a new set of orbitals that will produce the results that we want. Okay, so what it says is that when the bonds are forming, not before, but when they are forming, these two orbitals mix and they make a new set of orbitals. Right? So we know that each one of these, out of the P's, we can have three, right? We can have an X and a Y and a Z. And of course, you can only have one of these. So we got 4 atomic orbitals to start with. And we need 4 hybrid orbitals that will be equivalent. So we just base our name upon the atomic orbitals. So now we're going to produce hybrid orbitals here that are composed, each orbital, we're going to have 4 of them. Right? You got 2 here and 2 here, because they're 2 electrons, 2 electrons. We have 4 hybrid orbitals that are composed of the S's and 3 of the P's. Okay, we need 3 plus this 1 to give us 4 orbitals. Now we've got an orbital for that direction, that one direction, that direction. Okay, that's a hybrid orbital. This is one type of hybrid orbital. Let's see. But that's nothing new, except to say that the atomic orbitals were developed using quantum mechanics. Right? And we didn't go into a lot of detail about that because the math is just too much. But we're still using quantum mechanical equations to generate these 3 hybrids. So it's not just a figment of Pauling's imagination. He's got mathematical backing for producing this set of orbitals using the quantum mechanics. All they have to do is just tweak the equations, use the right set of numbers, and out pops the chi-squared electron distribution for these 4 orbitals. Right. Now remember, this happens only when the bond starts to form. Otherwise, carbon doesn't need it. And it's not something that carbon goes around with just waiting for something to happen. Okay, so this sp3 hybridization generates 4 hybrid orbitals with 109.5 degree angles. That gives us a tetrahedron and satisfies the requirements of the localized electron model in the valence bond theory. What we get in terms of energy is an orbital that is somewhere between the S and the P. The S orbital is a little bit lower energy than P, but the hybrid orbital is in between. And since we've got 3 P orbitals at this level and only 1 S at this level, then the energy for the sp3 is just a little bit below the P's. That's what we're trying to show here. All right, so those atomic orbitals on the left go into making the hybrid orbitals on the right. And that's what the quantum mechanical equations spit out. That distribution, that orbital shape and direction. Okay, so now as the bond forms, you get that hybridization and you get the structure that we need, which is tetrahedron. Okay, how about the ammonia molecule? Let's see if it works on other molecules. This definitely satisfies the requirements of methane. How about ammonia? Right, ammonia is this, H3, and we've drawn the Lewis dot structure for ammonia before. It has a nitrogen there. It has a hydrogen in the back. It has a hydrogen over here, and hydrogen over here, and it forms that triangular base. Right? And then the apex of the tetrahedron has a lone pair in it. Right? So the electronic structure is tetrahedral. Right? The molecular structure then, but is different. And that is a trigonal pyramid. Okay, all we have to do is cover that up, and now we get this triangular based pyramid. Okay, so if it's tetrahedral, that means we start with a bond angle of 109.5 degrees, but we know that it's going to be less than that. It's maybe 107 degrees because of this lone pair. Remember what lone pairs do? They balloon out and they put pressure on these bonds. But it's still technically a tetrahedron of sorts. All right. Oops. Okay, we've done that so far. Right, now we know that this is the Lewis dot structure. We have three pairs. The bonds are actually here, here, and here. Okay. Now, we know that nitrogen has 7. Instead of carbon is 6, nitrogen has 7, which would be 1s2, 2s2, 2p3. Right. We're only interested in the valence for this model. So, how many, if we're going to hybridize this thing like we did methane, the carbon in methane, how can we do it? Well, one of the rules is the number of bonds that go into a hybridization have to be exactly the same number that come out. So if we go in with 1 here and 3 here, we have to come out with 4. If we're going to use them all, we got to come out with 4. So we have 4 sp3 orbitals. Okay. Now, how would that work with this thing? Well, we only need 3 of them. Right? We have one of them that goes out here. We have one of them that goes out here, and one of them goes back there, and then another one that takes the lone pair. Okay, so we're basing our model, our hybridization, upon all the electrons, bonding and lone pairs. Okay. So that's what it would look like. And the lone pair is in one unused sp3 orbital. We only need 3 of them. We're using 3 of them, 1, 2, 3 here, and the 4th one for the lone pair. But we still hybridized 1s and 3p's. Okay. Let's try a little more complicated molecule. How about C2H4 ethylene? C2H4. We start from the beginning. We have valence electrons for carbon, 4, right? 1, 2, 3, 4. So we have 2 times 4 is 8, and then 4 times 1 is 4. We have 12 electrons. So we draw the Lewis dot structure. We do like this, like that, and then we have 4 hydrogens here, 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 and here. Okay, 2, 4, 6, 8, 10. We got 2 more electrons. So we work from the outside in. Hydrogen can't take anymore, so we just put them wherever we want to. Now we want to make the octet for the carbons. 2, 4, 6, 2, 4, 6, 8. So if we take that pair and put it right here, now we've got a double bond between the carbons. And we still got 12 electrons. Okay, so this is our Lewis structure for ethylene. Okay, so what would the shape be for each one of these carbons? Because they have 1, 2, 3, 1, 2, 3 around each one of them. So they're going to have the same geometry, right? What would be the geometry if you got 3 groups? 3 groups, trigonal planar, right? Since they're lone pairs, then the molecular structure is also trigonal planar around this central atom, trigonal planar around that central atom, right? Notice that if this is trigonal planar, right, if that's in a plane, double bonds don't rotate. Right? So if this is in a plane here, that's in the same plane. This is a flat molecule. Okay, just a side note. What's the bond angle? Well, the bond angle is predicted at 120 degrees, right? 120, 120, 120 makes 360. Okay. So there's trigonal planar around each carbon and 120 degrees. Okay. How do we get that? Because we've still got that problem. We can't use sp3 hybridization to account for this one. Because sp3 requires a tetrahedron. Right, so let's put that up here. We've done sp3, and that requires tetrahedron. Okay. Now we've got a trigonal planar, which only requires 3 orbitals. Right? So we just hybridize 2 p's and 1 s. And sp2 hybridization will give us this geometry. Okay. One of the p orbitals is not used for this bond, that bond, that bond, that bond. Okay, so what about this double bond? That double bond cannot be in the same plane as the rest of them. So what you see is, you see this carbon here and here, and now this one has an unused p orbital on each one. So we get overlap here like that, and that's where your double bond comes from. So the sp2 hybridization gives us the trigonal planar, and then the unused p orbital gives us the double bond, the second bond. Because it's like, if this is the plane, then the p orbitals are actually sticking out like this, and this, and the overlap is here and on the backside. We'll talk about that in a minute. This second bond, this double bond, is called a pi bond. But don't worry about that right now. We're going to get to it in just a second. So that would be ethylene. Okay. So we've hybridized an S and 3 Ps. We've hybridized an S and 2 Ps. Now, the logical would say, what about an S and 1 P? Okay, that's where we're headed next. Oh, no, we're not. We're going to talk about sigma bonds and pi bonds. Okay. A sigma bond is between two atoms on axis. That is, it's electron density in the bond is on axis between the two atoms. So that means there can only be one sigma bond between two atoms. One and only one. Okay. The pi bond, on the other hand, is between two atoms off axis. So in other words, it has to work a little harder to get that overlap. Right? If you've got an atom here and an atom here, this is the sigma. And if there's a double bond, then there has to be some overlap, usually between p orbitals. Not always, but usually. And it has to work a little harder to get that overlap to work, right? Because it's got to bend over, so to speak. That means that the pi bond is weaker than the sigma bond, because the overlap determines the strength of the bond. There's more overlap in the sigma bond than there is in the pi bond. So that explains what we learned earlier, that when we have a single, double, and triple bond comparison, the single bond is a certain strength. The double bond is stronger because it has a single and a pi bond, but it's not double the single, because the sigma bond that makes the double is weaker than the sigma. So that's why this one is not as strong as, is not double that one. And a triple bond adds another pi bond. Right? So that it's not a linear progression, because the pi bonds are not as strong as sigma bonds. Okay. Like I said before, you can only have one and only one sigma bond. You can have two, up to two pi bonds that I know about. Now, I'm sure there's research being done on multiple pi bonds, but for our purposes, single, double, and triple is as far as we're going. All right. Now, when we look at I guess we're not finished looking at the sp2. When we hybridize the sp2, we get one of the two p orbitals left over. Right, so it's at exactly the same energy as its original p orbital, but the sp2 is is a lower energy level. In fact, it's a lower energy level than the sp3, because now it has one s and only two p's. So if you just do the averaging thing, there's more s than character than there is p, so it brings the level down. So, all right. This is what it would look like, right? The sp2 orbital is planar, right? So you're going to have something bonded with each one of those sp2s, and we have that p orbital that's left over. And it's right angles to the plane. Okay. All right. So this is what they look like, mathematically speaking. All right, this just restates the obvious. If an atom is surrounded by three effective pairs, a set of sp2 hybrid orbitals is required. And that's what we showed with ethylene. This is trying also to show you the ethylene model where you get the overlap of those unused p orbitals right in here, top and bottom. So that's just an electron distribution model. So the two electrons that are in the bond here, they could be anywhere above or below in that overlap region to form the pi bond. All the ones that are on axis, but with the hydrogen atoms, are sigma bonds here, 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 and here and here. Okay, let's try carbon dioxide. We've done carbon dioxide before, right? Going to be, well, 2, 4, 6, 8, 10, 12. Okay, I finally got there. Okay, so now we take these two, make a double bond, these two make a double bond. Now everybody's got an octet. All right, bond angle is 180 degrees because this is a linear molecule. All right, how do we get a linear molecule out of that? We need sp hybridization on that carbon. Sp means linear. So with sp hybridization, of the carbon, hybridized carbon, now we get two orbitals, 1, 2 out of this. We get 2 sp orbitals and 2 unused p orbitals. Okay, so we get the sp orbitals are here, sp, sp in this single bond, and this double bond here is from unused p orbitals there and there, and also on oxygen. And the other one is at the other angle with the other unused on the carbon. I think they show a better picture. So we have a pi bond on this side and a pi bond on that side, which are constructed of unused p orbitals for the hybridization process. And there's the energy spread. Okay, that's what makes it look linear. And this pi bond is at right angles to this pi bond. So if this one is in this plane, that one is in this plane. Let's see. Now, oxygen, on the other hand, is sp3 hybridized. It has 3 effective pairs. It has one here. So this is sp hybridized. Oxygens are sp2 hybridized. So that gives you 3. It gives you one that's used in the bond, and it gives you one for this lone pair and one for this lone pair. Okay. That's where the lone pairs reside on oxygen. And then oxygen has an no, I'm sorry. That's right. sp2 hybridized for oxygen. But we're going to show the overlap. No, we're not going to show the overlap. This shows the hybridization for carbon and for oxygen. Oxygen's sp2 hybridized. That means it has an unused p orbital. Right? And that unused p orbital has to be used for bonding with the carbon on this side and bonding with the carbon on that side. And these lone pairs reside in sp2 orbitals that are not used for bonding. They're lone pairs only. All right. Let's check out nitrogen. we've drawn nitrogen before. It looks like that. Let's see. That should be 5, 10, 2, 4, 6, 8, 10. Okay, I got that one right. So this is linear with respect to that nitrogen and that nitrogen. And it has 1 sigma bond and 2 pi bonds. So it's also going to be sp hybridized from nitrogen. Okay. And once we get that done, we have 2 unused p orbitals. Unused p from this side and that side makes this pi bond, and the other unused p makes this pi bond. Okay. All right, so we're still talking about the localized electron model of the valence bond theory. So when you have an sp hybridization, you have a linear molecule and the potential for pi bonds. Doesn't mean you have to have them. It's only when an octet is required that this extra double bond, triple bond in some cases, will complete the octet. And in that case, you have those available unused p orbitals to do that. How about PCl5? Right? Right, we're not done yet with hybridization. We know what this one should look like. Let's go ahead and do it the whole way through. Phosphorus would be 5. 7 times 5 is 35, so that's 40 electrons. Okay, so we have P in the middle. We have 1, 2, 3, 4, 5 orbitals. 2, 4, 6, 8, 10. That's 30 electrons. 2, 3, 4, 5, 6. 6 times 5 would be 30, right? So we've used them all up if we do that. So what's the electronic and molecular structure for this one? Right, if you have 5 groups, right, it's a trigonal bipyramid. Right? So we would have the triangle, and we would have something up here and something down here, chlorine here, chlorine in the back, chlorine here, chlorine here, chlorine here, and phosphorus in the middle. Okay, how do we get that arrangement from S's and P's? We don't. Right. Notice where P is. It's in the 3rd period, so it has access to d orbitals. So when we hybridize for this one, we need S, all 3 of the P's, and 1 of the D's. Which they, by convention, they put D in front. I don't know why. DSP3. DSP3 hybridization gives you 3, 4, 5, which would make it the trigonal bipyramid. Okay. And there's the shape and the bond angles. 90, 120, and 180. 180 if you count from here to here. If you count from here to here, it's right angles. And if you count from here to, say, over here, it's 120. Right, so you have those 3 possibilities. Let's see. Right. When you have access to 3D orbitals, then you can hybridize further. And in this case, we have to. That's what it would look like. Chlorine doesn't have to hybridize. I don't believe. Oh, yes, it does. Chlorine has to hybridize. sp3. Notice its shape. These electrons in here, including the bonding one, this shape is tetrahedral. All right, so chlorine has to hybridize also. All right. Let's take a short. Let me go. Let me go get those copies of the crossword puzzle. I'll be right back. Okay, next. We have this possibility. Xenon tetrafluoride. Right? Xenon has 8. It's a noble gas. 4 times 7 is 28. So it's 36 total. So we have xenon in the middle. We have these 4 fluorines. Like hydrogen. There we go. 2, 4, 6, 8. So that's 28. 2, 4, 6. 6 times 4 is 24, right? 4 electrons left over. Okay, so they have to go here. All right. So we have how many groups? We have 1, 2, 3, 4, 5, 6. 6 groups means octahedral. This is electronic. So that's what they mean by effective groups. What goes into the electronic configuration of a molecule? All right, so how do we get 6? How do we hybridize xenon to get 6? Well, we go back to the D, right? So now we need D2sp3, 3, 4, 5, 6. So this is octahedral. Okay, and we know this is going to be square planar, right? It's going to have that, like that, that. Xenon in the middle. It's going to have lone pair up here, lone pair down here, and fluorine on the square. Okay, so the bonds are going to be like this, 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 that, and this. Well, that's not a bond, that's a lone pair. Okay, so we're going to use 4 of those for the fluorine bonds, the xenon fluorine bonds. And the other 2 unused are going to be out here for the lone pairs. Okay. I think that's as far as we're going to go with hybridization. And they're all 90 degrees. All right, 2 Ds, 1 S's, and 3 P's. That's an octahedral shape. We know that it's not, if we're just looking at the 4 bonds, and we say, oh, that's got to be sp3 because we only need 4 bonds. Right? We know that's not true because experimental evidence says the bond angle is not 109.5. The bond angle is 90 degrees. So we know sp3 can't be it, right? The evidence doesn't support it. So in that case, we have to include the lone pairs in the hybridization in order to get this square format and 90-degree bond angle. That's the only way we can come out with this shape and agree with the localized electron model and hybridization at the same time to answer the question, why are the bonds 90 degrees? That's the only way you can get 90 degrees out of this situation. Right. So there's another. They don't bother to, like the chlorines, they don't bother with fluorine hybridization. But it does have access to p orbitals, so fluorine should hybridize also. All right, so there's a compilation of the number of effective groups, the VSEPR shapes, and the hybridizations required right there in one little table. It's all of this plus the number of effective groups. Right. We know that the groups for this one are going to be 4, for this one are going to be 3, and this one are going to be 2. This one will be 5, and this will be 6. This is groups of electrons. Any questions so far? Now this hybridization fix that Pauling proposed is effective at answering questions like, what are the bond angles? What are the shapes? Are all the bonds equal in strength and length? Those types of things. It doesn't, however, even though we use that energy diagram, it doesn't tell us exactly. We can't calculate the energies. It's not part of the model. It just won't work. So here's another possibility, HCN. Let's see. Yeah, that's what HCN would look like. It's still a linear molecule, and we're going to use sp hybridization on both carbon and nitrogen to get there. Let me see, how much more do I have before my scheduled break? That's what I'm interested in. Not too far, 3 slides. Okay, I'm gonna let you work that one out for yourself because I am still running short of time. So there's your sigma. There's a sigma bond with hydrogen. Now, here's a stupid question. Can hydrogen have pi bonds ever? No. Hydrogen cannot have pi bonds because it doesn't have access to p orbitals. Right? It's only in the first period. So you'll never have a double bond or a triple bond with hydrogen. All right, so there's your sigma. There's a sigma between carbon and nitrogen. It's on axis, just like always. And then your pi bonds are off axis. Okay, let's see. We've already done ammonia. Let's see, is it going to be given to us? Yeah, there's ammonia. sp3 hybridization. Are we going to go across? Yeah, we're going to go across. So let's do SO2. Okay. Sulfur, same as oxygen, has 6. So, and that's 12. That's 18 total. All right. So we do our Lewis structure. That's -4, 14, 2, 4, 6, 8, 10, 12. And then 14. 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10. Wait a minute. Oh, yeah, 12, 14, 16, 18. Okay. Now we need to make an octet. This is one where we've used a trick in the past already, right? Resonance. Because which way does this, we can't use these because they've already got octets. If we put this one over here, that will give sulfur an octet. Let's see. Wait a minute. No, we can't. That would fix the problem. We've got to use one from over here, or a pair from here, or a pair from here. And so we have the possibility of this or this. Remember? Okay. And then they resonate. Either way, what's the hybridization on sulfur? 1, 2, 3 groups, right? sp2. That means trigonal planar. Let's see, it asks us bond angles. Okay, bond angles 120 degrees. All right. Oh, it didn't ask shape, just hybridization. So sp2 hybridization at 120 degree angle for SO2. All right. Let's see. I guess krypton difluoride is our next one. All right. Krypton's 8, fluorine is 7 times 2 is 14, which is 22 total. Right. Krypton, fluorine has 2, 4, which is 18. 2, 4, 6, 8, 10, 12, which is 6. 2, 4, 6. Okay. So what's the hybridization here? 1, 2, 3, 4, 5. We have 5 groups, which means we need 5 hybrid orbitals. So we need D, 1, 2, 3, 4, 5. DSP3. So that means we have the possibility. Well, actually, bond angles here. Where are those fluorine going to be? And if we draw the triangle here, and then we put like that, krypton in the middle, where do we put the lone pairs? In trigonal planar, right? In octahedral, we put them out here. But in trigonal bipyramid, we put them on like that. So the fluorines are going to be here and here. The bond angle is 180 degrees. Okay. Oh, we just added a little comment. It's nonpolar. Okay. DSP3. We need 5 orbitals. 1, 2, 3, 4, 5. 5 hybrid orbitals to satisfy that molecule. And I'll say it again, if I haven't said it before, what we have to do is match our theory to the results. And the experimental results say that krypton difluoride has a 180 degree bond angle. It's nonpolar. So that's the only way we can answer it with our current theory. CO2, we've already done that one. It's 180 degrees sp hybridization. ICL5, how about that one? ICL5. So that's 6 times 8, 6 times 7 equals 42 electrons. Okay. Iodine in the middle. 1, 2, 3, 4, 5. Fluorine. Okay, 2, 4, 6, 2, 4, 6, 8, 10. 2, 32. So that's 6 times 5 is 30. Equals 2 more left over. So we have to put them there. All right. This is 6 pairs. That's octahedral. Which means what? We need 6 hybrid orbitals. D2, sp3. 1, 2, 3, 4, 5, 6. And what are the angles here? Well, where does this one go? Well, it's going to go like this, iodine in the middle. We're going to have possibilities here and here for our octahedron. Remember, in the octahedron, the lone pairs go up here like that. So we've got chlorine here, 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 here. And that means there to there is 90 degrees. And there to there is 90 degrees. So 90 degrees is the only possibility for this one. And ICL5, we just did that one. 90 degrees is the only possibility for that one. And it's D2sp3 because we needed 6 positions for 6 effective pairs. Okay, so when we use the localized electron model, we know we have to start with the Lewis dot structure. Then we have to use that information to determine the electronic structure with the VSEPR model, and then the molecular structure. From that, we just cover up the lone pairs and what's left over. And then, since we know how many lone pairs are required to make that structure, then we can use that to tell us what hybridization is required. So if it's 2 groups, you need linear. If it's 3, you need trigonal planar. sp2. 4 groups, you need sp3. 5 dsp3 and 6 d2sp3. It's fairly straightforward. All right, here's some of the limitations. The assumption in the localized electron model is that the electrons are localized on the atoms. And the only reason they form bonds is because they share orbital space. But the electrons still belong to each atom. That's one of the major drawbacks. And some of the fixes we've had to do, major fix was resonance. We couldn't draw the structure properly because 2 or more acceptable Lewis structures were available. So we introduced resonance. Well, it was introduced. The other one is well, okay, I'll take these in order. What do we do with molecules that have unpaired electrons? We didn't cover too many of them. There was one that had an unpaired electron, free radicals. What do you do with those? Well, we were just counting them as groups, right? And an effective singlet. But that was just a stopgap. That really doesn't tell us much about the molecule. Those free radicals are really difficult to deal with in this model. It gives us no direct information about bond energies. The localized electron model and valence bond theory says nothing about the energies. It can't. It has no way to calculate the energies of the bonds. We have to determine those empirically at this point. That's all we have going for us. And then, I think I left out a point. The localized electron model, unless we hybridize, does not give us an accurate representation of the true bond overlaps. And if we overlap the orbitals as determined by electronic configurations for individual atoms, it doesn't work for every case. So that's where hybridization came in. So those 4 points are shortcomings of the localized electron model. Okay, so now we're going to pause and we'll pick this up on Thursday and finish out with the molecular orbitals.